So now let's talk about these particles that we have in nucleus. What we have uh, is protons and neutrons. That are the constituent particles of this nucleus. And if I have to I would like to suggest some of the important properties of these protons which are there. The very first thing is that they are positively charged. So they are positively charged. And this is the first thing. The second important thing is that the magnitude of charge, the magnitude of charge for this proton is 1.6 times 10 to the power of minus 19 coulombs. And the mass of this proton, if I look for its mass is nearly 1.6726 times 10 to the power of minus 27 kilograms. And if we convert that into atomic mass units, that comes out to be 1.007276 atomic mass units. And so we go here up to the fourth decimal place, because there is a very small difference in mass of proton and mass of neutron. And then this proton has spin. It has spin, and it has its intrinsic spin, and that spin is it is 1/2 of h cross, and that is h by 4 pi. And this h is known to be as Planck's constant. It's Planck's constant. All right, and then what is the number of these protons? Their number gives us the number of protons simply gives us the atomic number. It gives us the atomic number of the atom, and this proton has it has a magnetic moment. It has a magnetic moment, and this magnetic moment is calculated experimentally, and its value is nearly 2.79 nuclear magneton. In atoms we have Bohr magneton, but here we have nuclear magneton. So these are some of the fundamental properties of these protons. And then comes the point of neutrons, and these neutrons they were discovered in a very peculiar way. And this neutron is also a constituent particle of the nucleus, and it was discovered by, I always forget. So it was discovered by James Chadwick in 1932. So what was the basis of discovering the neutron? Was that Chadwick, what he did is basically he chose a material with some paste on it. We have a silver plate, and it has a polonium that's polished on silver, and from here what we get is the alpha particles. We have alpha particles, and these alpha particles are subjected to this beryllium metal, and after penetration, what we see is we have the penetration of these alpha particles. What he used was the paraffin block, and what he observed, what was coming out of it, was protons. So the penetrating rays that were emerging from beryllium metal, they were certainly permitted to fall on this upon this block of paraffin that we have, from which protons were found to come out with high speeds. They were coming up with high speeds. They were coming up with high speeds. Uh, and, and from fundamental laws of energy and momentum conservations, Chadwick showed he showed that the penetrating of rays that was emerging from this beryllium metal, they were neutral particles having no charge, with mass nearly equal to that of protons. And what he showed here is that these penetrating radiations are not composed. They are not composed of uh, of 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 protons, because the particles present in these radiations were having much lesser energy than that of the protons that were coming out of this paraffin box. So this way he could discover these neutrons inside the nucleus. And if we choose He4, which is an alpha particle, and use a beryllium 9 for, what we get is we get C612 and a neutron. And this reaction is this reaction can be illustrated. You have an alpha particle and you have beryllium and 9 and 4, and it converts into C12 and 6. And in addition of that, what we have is a neutron, and this neutron does not have any charge. It's a chargeless particle present inside the nucleus. Now these neutrons they also have properties. They have some important properties, and to illustrate them, the very first thing is that neutron has no charge. It has no charge. This is the first thing, and the mass of this neutron, is 1.6748 times 10 to the power of minus 27 kilograms, and that comes out to be 1.008665 atomic mass units. Then, being neutral, this neutron can neither be attracted or repelled by the nucleus of an atom, because it has a neutral charge. So it can penetrate. Its penetration power is deep into the atoms of targets. So if we have targets, choosing neutrons is good, because they can penetrate to the deeper regions, because they don't have any charge, so they will not interact with the charges that are available there in terms of atoms. And then the important thing, neutron has low ionizing power. Okay, ionizing power, we understand the amount of energy that's used to ionize an atom. And neutron inside the nucleus, it is stable inside the nucleus. It is stable, apart from some of the nucleuses about whom we'll be talking in future. So if we have this neutron to be unstable, when this neutron is unstable, what happens is that it decays. This neutron can decay. So if I have a neutron, it can decay into a proton and an electron and an anti-neutrino. So this is how the reaction takes place for a neutron. If this neutron is present in some unstable nucleus, so when there is instability, this neutron can undergo a reaction to be converted into a proton and electron, which comes out to be known as beta particle and an anti-neutrino. And the mean free life for the free proton is for the free proton, it's nearly 17 minutes. So that's nearly 1,000 seconds. A free neutron can live like a neutron for this much of time. And the speed of these thermal neutrons that we can produce, these speeds are They are high. They are of the order of 2200 meter per second. This is the speed, and the energy of these neutrons is 0.025 electron volts. Now these thermal neutrons are most suitable for causing nuclear reactions. So they are the basis of causing nuclear reactions. And to end this video, this neutron has exactly the spin, and it has its intrinsic angular momentum, and that intrinsic angular momentum is h cross by 2. And it has a magnetic moment that has been calculated experimentally, and that magnetic moment is nearly minus 1.91 nuclear magnetons. So these were some of the basic important properties of the particles that are present inside the nucleus in terms of protons and neutrons.